So here we see a setup for generating the electromagnetic wave. So here is a energy source, just like something a battery, something like that. But yeah, and it provides some electrical energy, and then this is a RLC circuit, so it will oscillate with a frequency near. The frequency will be around 1 over square root of LC. So not proportional, should be approximately 2 pi LC. So if you're curious about this value, you can check back chapter 31. We have not covered it this semester, but I have posted a link in the last semester, so you can check it back. And so this is a transformer, so it can transform this energy into here, so that it can match the resistance, match the impedance here. And then this is actually a antenna, a electric dipole antenna. So it treats like this as a transmission line, so that this one will transmit the EM wave. Okay, so an arrangement for generating a traveling electromagnetic wave in the shortwave radio region of the spectrum. An LC oscillator produces a sinusoidal current in the antenna, which generates the wave. Okay, so this is somehow like the source of the EM wave, and when it transmits the EM wave, this is the wave. These are the wavefront. So if the points are close enough, then you will feel like, oh, this is a point, and then they are a concentric sphere, and yeah, somehow like that. So the wavefront is somehow like the part of a sphere. But actually, if the point is far away enough, then we will assume that this is a circle, a sphere with a very large radius. Then we will assume maybe this part is so-called a plane wave. If we have this assumption, then the mathematics will become much elegant. Yeah, and in previous chapter, I have mentioned another term called the far field. They are quite the similar concept here. So if it is far enough, then we can make many simplification, because sometimes tends to infinity, then the finite term will be vanished if it is added with this radius. Okay, so here it tries to tell you that if we observe the EM wave, it will be something like that, starting from here, part A. Okay, so suppose E cross B. Okay, suppose the EM wave is propagating out of the page. So you can imagine. Yeah, this is the front. So suppose the EM wave is propagating in this direction. Then if you are able to measure the E field and B field of the wave, then you will observe that the E field at this moment is pointing upward. The B field is pointing to the left at this moment, at the very beginning. And sometimes later, delta T maybe, sometimes later, then the magnitude of the E field and B field becomes smaller with the same ratio. So this triangle and this triangle are similar to each other. Yeah, so they become smaller, and then at this point, both E field and B field become zero. And then sometimes later, the E field point to the opposite side, and then the B field also point to the opposite side. And then here, the E field becomes larger, but point to the opposite side. B field the same case. And then go back to here, and then become smaller, and then zero. And then point to the original direction, and then with the same magnitude with this one, and then become back to this case. So it will loop like this forever if there is no loss between. So here it says the electric field E and the B change with time as one wavelength of the wave sweep past the distance point P. Yeah. So it also mentioned the term plane wave here. If we assume that this point P is far away from the antenna. Okay, here it mentioned there are 4 characteristics for the EM wave. So the first one is that the E field and B field are always perpendicular to each other, to the direction in which the wave is traveling. I just mentioned the propagation of the wave is pointing out of the page. So the E field is perpendicular to is on the plane. So just mention the direction of the wave is pointing out of the page, which is always perpendicular to the plane. So as much as E field and B field are always on the plane, so you can see usually maybe I will just mention it later. So the propagation of the wave, we will use S vector, the pointing vector, to mention the direction of the wave and the magnitude of this pointing vector. Okay, so it is always perpendicular to E and B. So as this one, even though this is 0, but actually the wave is still propagating. Yeah, so maybe this is some of the exceptional case. So all the way they will have traveling with a direction perpendicular to the E field and B field. And the second one is that the E field is always perpendicular to the magnetic field. So you can see here E field perpendicular, pointing to the opposite side, still perpendicular to each other. Okay, so which means that the E field, B field, and also the pointing vector are always perpendicular to each other. Okay, and then the third one is the cross product E cross B always give the direction in which the wave travel. So at the very beginning, if you feel that I use a right-hand rule very quickly to say that the EM wave is pointing out of the page, because I remember this property. The E field cross B field will be the direction of the pointing vector. Actually, the pointing vector, some page later you will see that the pointing vector is actually E cross B over mu naught, if I remember correctly. Just check it some page later. Okay, so the fourth property is that the field always varies sinusoidally. Actually, here we cannot see the sinusoidal here, but actually, if you take a small delta t, well, actually not easy to read it here, because we only have a point. Somehow, like if you have a sine wave, you pick 1 point, 2 points, 3, maybe something like that. Yeah, in signal system, you know, or the sampling theorem, something like that. Yeah. Yeah, but anyways, the field always vary sinusoidally. But yeah, actually, it's not very true, because it is a simplified case. When it is not a sinusoidal, then yeah, also in signal system, you know, you have Fourier transform. Any waveform can be you can use the Fourier transform to transform the non-periodic signal and then decompose it into many different sinusoidal waves. Then actually you can just make everything separately. You can consider different frequencies separately, and then you finally add them together. Because sometimes the system is linear, then you can do this thing. And that's why you need to learn Fourier transform in signal system. And moreover, the fields vary with the same frequency. The frequency won't change, and the phase will vary with the same frequency and in phase with each other. They will be in phase. So the E field take the maximum, and also the B field take the maximum. They are both zero together, so they are in the same frequency with the same phase. Okay. Somehow like this. This is in phase. Yeah. So they will have the zero crossing point together. Okay. So here it mentioned that the E field and B field will be with this form. We have this form. Actually, after the slides of this chapter from the textbook, I will have supplementary to tell you why it will be like that. The textbook only tells you what it is, not mentioning how to derive it. Actually, it mentioned a special case for it, but yeah, I will have a supplementary look after this chapter. And yeah, so far, and you can just accept it is right, and I will tell you why it will be like that later. So here it says the magnitude of the E field is the magnitude. Sorry, it should be the E field. The E field is a function of the x. X is the position. X is the x position, and then t is the time. It's a function of position and time. K is a constant. Omega is a constant, and Em is the amplitude of the E field. And similarly, we have the B field, just changing E to B, Em to Bm, like this. So Em, Bm are the amplitude of E field and B field. And then K is called the wave number. K is called the wave number. Wave number, the SI unit is meter inverse, 1/meter. And then omega is the angular frequency. It has this relationship. K equals 2 pi over lambda. Lambda is the wavelength. Yeah, lambda is the wavelength. So you can imagine 2 pi over lambda, which means that if lambda is larger, K is smaller, which means that K is proportional to the unit length. You can how many waves you can count. So this is called a wave number. So if the lambda is larger, K is smaller, because for a unit length, just say 1 meter. If the wavelength is longer, then maybe you can only count 2 of the wave. Just say if it is 1 meter. Maybe if the wavelength is long, so this is the wavelength, or you can only count 1 wave in the unit length. If the wavelength is shorter, just say 2 times shorter. So this lambda is shorter. So you can count more number of waves in this unit length. So this is called the wave number. And also you can see that I mentioned before C equals F lambda. And here we have we have k equals 2 pi over lambda, which means lambda equals 2 pi over k. 2 pi over k. So here we can have f times 2 pi over k. And actually, omega is 2 pi f. So this is called the angular frequency. This is the frequency. So multiplied by 2 pi will be the angular frequency. So here we will have omega over k. Omega over k. So you can check here. This is omega, this is k. And then kx minus omega t for sine function. Sine and cosine is fine. It's just a 90-degree phase shift between cosine and sine. Okay, so yeah, so we briefly explain this variable for the EM wave. Okay, so here it also mentioned that the speed of the wave is omega over k. However, because this is an electromagnetic wave, its speed is given in the symbol c rather than v. Usually we use v to stand for the velocity or the speed. But for the speed of light, it has a special name because it is unique. It cannot change in different inertial reference frame. We'll mention that in next chapter, chapter 37, about the special relativity. That c has the value given by this expression. I think I've mentioned that before. C is 3 times 10 to the 8th power meter per second. And this is the permeability, this is the permittivity, and then take the square root of 1 over this term. So if you need a more precise value, it is 2.998 times 10 to the 8th power meter per second. So yeah, for the speed of light, you can consider something like sine kx minus omega t. So this is like we have a EM. Okay, so suppose we consider kx minus omega t equals a phase, just say 0. If we have this term to be 0, which means sine of 0 will be 0. So you can see here, suppose a wave, it is propagating, which means that you are observing maybe this point. And suppose we have t equals 0. T equals 0. Then x should also be 0. Then x should be 0. And if we have now t equals to capital T, then x will be omega t over k. Omega t over k. So if you just divide, this is x over t. This will be the velocity, and we use c to represent the speed. So it will be omega t over k over t, which is omega over k. So we have this expression. The speed of the wave is omega over k. This means that you will feel like this point is actually moving. This actually moving. After some time, it is moving in the speed c. With the speed c, and then you see this point moving because I try to keep this term to be 0. And we see when t change, how does x change. Okay. So so here it also mentioned that the amplitude of the E field and B field will keep to be a constant. So this constant is the speed of light. It's the speed of light. I will also mention how we can derive it later after this slide of this chapter. But yeah, actually they will keep a constant ratio, just like this for this moment, these two triangles are similar to each other. All these triangles are similar to each other. So they keep the same ratio between the E field magnitude and B field magnitude. Okay, so just mention that. So this is the Poynting vector. I forgot. I remember it correctly. So the Poynting vector is actually the rate per unit area at which the energy is transport. Okay, so which means that within a unit area, within this area, how much energy is transported with the EM wave? Because in chapter 25, you know that the E field will store some of the energy, or if the E field exists, there must be some energy to generate this E field, and also for the B field. So if the EM wave is propagating, there must be some energy to transfer. Just like if there is a sun, you will feel very hot, something like that. So and actually, of course, the light is a sort of EM wave. Okay, so actually, via an electromagnetic wave is given by the Poynting vector. So we have a E cross B, so you can use the right-hand rule to determine the direction of the Poynting vector. And then there is a normalized vector 1 over mu naught here. Okay, so I will also tell you why later. And here it mentioned a property called the intensity of the light. 是强度. So the time average rate per unit area at which energy is transferred is S average. So you can just take this amplitude divided by square root of 2, something like that, and so S average will be E average times B average over mu naught. And then we will have, if you still remember here, EM BM equals Z. So we will also have E average over E average equals Z. Here, I think in chapter 31 it used the term ERMS rather than E average. But actually, I think it refers to the same quantity. So ERMS should be EM over square root of 2. This one should be BM over square root of 2. So actually, the square root of 2 just cancel each other. So we also have E average over B average to be C. So which means that we have a B average equals E average over C. So we can plug this one into here. So we have E average square over mu naught C, which is this one. or we can use ERMS here. I don't know why it uses average for the S. Okay, but actually I think they refer to the same thing. So this is the intensity of the EM wave. Yeah, it also mentioned that here. Okay, so from another point of view, the intensity is like from the source it generate the power PS. PS is the energy per unit time. So this energy will propagate in all the direction. So for the first moment, it goes to here, and then some with the same moment later, then this sphere become larger and larger. So for every point, it will be equal to the PS divided by the surface area of the sphere. So this is the surface area of the sphere, 4 pi r squared. And it will be the intensity, because this is the energy, that I think the energy per unit area. Okay. So here we have a sample problem. So here it says, when you look at the North Star Polaris, 北极星, so you intercept light from a star at distance 431 light year, Ly, light year, and emitting energy at rate 2 times that of our sun. Neglecting the atmosphere absorption, find the RMS value of the E field, B field when the starlight reaches you. Okay, so here we have I equals PS over 4 pi r squared. I'll just use the formula in the previous page, and then PS is and then I is also equal to ERMS square mu naught C. Yeah, so we just make use of this one, and they are equal to each other. So you can make some calculation, and actually we need to calculate what is 431 light year, 431光年, 431光年. So it is a unit for the distance. Yeah, so R equals 431 times 3 times 10 to the 8th power, so this is the speed of light, times 3,600. So 1 hour has 306,000 seconds, and then each day we have 24 hours, and then 365.25. We also consider the leap year, and so this is 4.08 times 10 to 18 meter. Okay, so we use the light year to specify their distance between stars. Otherwise, we will have this kind of a 10 to a huge number power. Okay, so this is R, and then we can do something for this one. We can have ERMS equals, we just move this term over and then take the square root on both sides. So we have a PS mu naught C, and then over 4 pi r squared, and then take the square root for the whole term, and then we can just plug in all the values. So P sun is 3.9 times 10 to the 26th power, and it is 2.2 times 10 to the 3rd power times stronger, so we multiply it by 2.2 times 10 to the 3rd power. So this is PS for the polaris. Okay, so multiply by mu naught over 4 pi is 10 to minus 7. Okay, and then times 3 times 10 to the 8th, and then all over r square is 4.08 times 10 to the 18 power quantity square. Okay, and then take the square root for the whole term. So this is 1.24 times 10 to minus third power. You can use V over M or N over C for the SI unit of the E field. And the BRMS, we can simply use ERMS over C to calculate it. So we have 1.24 times 10 to minus third power over 3 times 10 to the 8th power. So it is 4.1 times 10 to minus 12 Tesla. So this is the RMS value. So this is the RMS value for the star. So you won't feel, or the star will make you feel hot because this E field B field is so small. If you're interested, you can try to find the distance between the sun and the earth. Then you will be able to find the intensity of the sun. Then you feel the difference between them. Or even though the Polaris is the energy transmit from the Polaris is almost or more than 2,000 times larger than the sun, but it is much far away. If I remember correctly, the sun and the earth only takes 8 minutes, I think, around 8 minutes, if I remember correctly. The distance between the sun and the earth is around 8 minutes, so it is much smaller than this one. Okay. So here it also mentioned the radiation pressure. I don't know much about it, so I just mentioned the formula here. But actually, why it tells it is that the EM wave will have the duality, 就是波粒二象性. So actually, the pressure is some sort of particle characteristic, and the EM wave is of course the wave characteristic. So it just mentioned it here. Actually, I have never used it before. I have never see this equation before I teach this course. So just a minor thing, I think. So when a surface intercepts the EM radiation, a force and pressure are exerted on the surface. Just like the sun, when it's summer, then you feel the sun is so hot, and maybe if you have a spotlight shooting on you, then you will also feel it's very hot. So the radiation is totally absorbed. If the radiation is totally absorbed by the surface, the force is this one, IA over C. So it is of course proportional to the intensity of the light, and also proportional to the area, because if you have area, then you feel larger force, and then all over C. So for the second case, if the radiation is totally refracted back along its original path, the force is 2 times larger, because you can imagine if this is the object, so this is the force, F equals IA over C. So there may be some momentum. Here. not good to write MV because for the for the photon it has no mass, so it has some momentum. Is okay. So if it is totally absorbed, it totally absorbs this one. But if it is P and we totally refract it, then the force should be 2 times larger because you should keep the conservation of momentum. So this refer to F over IA over C. This refer to minus IA over C. So if you take the difference between them, then there will be 2 times of this value. Okay. So the radiation pressure is the force per unit area. So you just divide by A, so you have I over C, 2I over C. So nothing special here. Okay, so next we consider a interesting phenomenon for the EM wave called the polarization. So it says the EM wave are polarized if the E field vector are all in single plane, called the plane of oscillation. The light wave from the common source are not polarized. That is not, they are unpolarized or polarized randomly. So in this case, this one is unpolarized. So you can see the E field are oscillating for different in different direction, even though the pointing vector is pointing either into the page or out of the page. So for this case, all the E field are propagating in the y-axis, and the B field are oscillating in the z-axis. So y cross z will be positive x. So the wave is propagating in positive x direction here. So it called this one the plane of oscillation. And if you see this one in this from this direction, you will see the E field are propagating, oscillating like this. You will not see the other direction of the E field like this one. Okay, so it is also possible to mention it like this. So if you combine all of them together, so you will see some of it are in the vertical direction and some of them are in the horizontal direction. So this is unpolarized. Yeah. Okay, so this is the interesting stuff. So so this is called the polarizing sheet, or we can call it the polarizing filter. 滤光的. So if the original light is initially unpolarized, the transmitted intensity is half of the original intensity, I0. Yeah, so if originally it is unpolarized, it has both vertical direction component and horizontal component, and if it passed through this polarizing filter in the vertical direction, then only the vertical component can go through. So we assume that half of it is vertical, half of it is horizontal. So only half of it can go through this filter. So we have I equals half of the I0. I0 is the intensity here. This is I. Okay. So more interesting is that if the original light is initially polarized, which means it is already polarized, the transmitted intensity depends on the angle theta between the blah blah blah, and then the relationship will be like I0 cosine square of theta. So we have a square here. This is not show you, so yeah, we need to consider this a square here. Yeah, which means that if here if E is polarized in this direction and then pass through the polarized filter in vertical direction, then there is an angle theta between them. Then after passing through this filter, the intensity will be multiplied by this cosine square of theta factor here. Okay, so yeah, let's have a break first and 10 minutes